Hello, everyone. Hey, let's talk about cycloalkanes. These are molecules, alkane molecules, that have been joined end to end to form a ring. And I remember one time in class, I may have slurred my words and someone raised their hand and said, "Did you say psychoalkanes?" Yes, those crazy molecules, psychoalkanes. No, cycloalkanes. Alkanes are formed into rings. And then you can do whatever you do on a normal alkane. You can decorate with branches or halides, or you put other functional groups in their place. They're just simply other molecules nature likes to make. What we'll do is name them in this video. So again, we're just going to go back to our standard naming procedure, IUPAC nomenclature. And the one thing we're going to add is that now the molecules are in rings. Not a big deal. One key concept to kind of keep things straight is we have to remember that if you have a branch, that's probably a chain, and you have your ring, those we're going to have to separate in our mind. When you are naming the cycloalkanes, a carbon that's in a ring is not part of a chain. Some people say you can't double count the carbon. That makes sense. And in our task today, and on the next exam, is to be able to name molecules given any combination of rings, chains, or halides. That's going to be on exam 1. And then if I give you a name, I want you to be able to draw them. Okay. Here are the naming rules. We saw that in the previous video. And right here, what we're going to do is just mouse. Right here, just going to add the prefix cyclo to say, hey, the parent now is wrapped up in a chain. So over here to the right, we have 4 examples, right? So 3 carbons is propane. And if it's tied up in a ring, triangle, if you will, then the proper name is cyclopropane. Butane's 4 carbons. Let's see, Mabel eats peanut butter, right? The butter reminds us of butane. Cyclobutane is 4 carbons in a ring. Cyclopentane, and cyclohexane. And they're more common than you might imagine. So what are we going to do with this? Well, let's see, in that previous video on naming, we saw the full set of rules. I kind of abbreviate them from the standard IUPAC rules, kind of my note-taking, but really what you need to do is find the longest chain or ring. That's step 1. And if you have a ring, add the prefix cyclo in front of the parent name. That's kind of modifying step 2. So we'll take a couple notes here. So we add cyclo when there's a ring, when a ring. And then we're going to do everything else the same. Well, let's see some examples. Well, let's start with, what if we have, let's get 3 carbons into a ring. And off of this carbon, let's just make a chain. Kind of sloppy. Need to warm up my hands, get them going. Okay, step 1, find the longest chain or ring. Okay, so actually I might swap colors. That might be effective. Let's go to orange. Let's see here. Okay, step 1, find the longest chain or ring. I like to find the rings first. Okay, so here's a ring of 3, the triangle. And now I must realize that this carbon that's part of the ring cannot be part of a chain. Ring carbons are not chain carbons. So we have a ring of 3 carbons. And then we have 1, 2, 3, 4 carbons in the chain. And so the longest chain or ring wins. So the chain wins. That is the parent. That was step 1. We found the parent. It's the chain of 4 carbons. Step 2 is to name it. Mabel eats peanut butter. Butter, 4 carbons. 4th word in Mabel eats peanut butter. Yeah, so butter, butane. And it's not a ring, so the full parent name is butane. That's step 2. Step 3, we got to number the parent. Okay, let's do that. All right, so we need to number it from the end of this butane chain. There's a left end over here, and there's a right end over here. Which one is closest to the branch? Yeah, it's a funky branch. This ring is the branch. This is carbon 1. It's closest to that decoration, if you will, on butane. So we have to number it in this manner, starting on the carbon of the parent closest to our first branch, a ring of 3. So step 3. Step 4, name and number the branches. Okay, so what is this thing? Well, 3 carbons is called Mabel eats peanut. That reminds me of propane. Propane is the parent name though. So if we have extra carbons, branches, we don't say propane, we say propyl. We change the YL ending, change the ane ending to a YL ending to represent the fact that these carbons are not part of the parent, they are a branch. Ooh, but this propyl group's special. It's been wrapped up into a ring. So add the prefix cyclo, make that letter O big enough so it all crams together into one word. And that's it. And then it shows up on, that's the name. It shows up on carbon 1 of butane. And then simply step 6 is list all the branches. There's only one branch. It's a cyclopropyl group. And shove the parent name next to it. We're done. 1 cyclopropyl butane. Okay, what if we have, how about, let's name this molecule. Let's do that, and this. Sure, why not? You can pause the video and name it on your own if you'd like to try. Swap the colors again. Back and forth I go. Okay, let's scroll up so we can see step 1. Step 1 is find the longest chain or ring. So I start with the ring. There's a ring of 5. And once I found the ring carbons, I cannot count them as part of the chain. So over here, I got a 1 carbon chain. Let's see, our chain of 1. And then over here, there's a 2 carbon chain. And the longest chain or ring wins. Well, the ring wins this time. This is the parent. And now we'll jump to step 2. The parent is a ring of 5 is pentane, but add the prefix cyclo. And we got the parent name cyclopentane. That's step 2. Step 3, number the parent carbons from the end closest to the first branch. Okay, we have a choice here. If we start on this carbon, we can immediately find a branch. So maybe this is carbon 1. Or over here on the right, we start numbering the ring here, that's carbon 1, immediately at a branch. So that's a nice pattern that shows up when you're dealing with cycloalkanes or any ring compound. When it's time to number the ring, you always have a group on carbon 1, right? So you can, the ring doesn't really have a beginning or end, so you can choose any carbon of the ring to be carbon number 1, and to get the lowest number, start at a branch. Unfortunately, here there's 2 choices. Do we start on this carbon with a branch? or the carbon on the right? Do we start there? Well, what's our tiebreaker? Go to your second branch. Okay, so if I start on the left side, this could be carbon 1, and then I'll go across the top 2 and then 3. I don't want to go around the bottom, right? So if I say, hey, 1, 2, 3, 4, ooh, that's too high, right? The objective is to keep your golf score down. You want to get to the next branch as fast as you can, so you want to go across the top. So if you start on the left side, the numbering would be 1 and 3 for where the branches are. But if you start on the right side, then carbon 1 is right here at this group, and then you go counterclockwise to get the number 3 where the other side, the other branch is. It's a tie again. Okay, and so and that's it. There's not a third branch to break the tie. So now we have to go alphabetical order. So what's the name of this group? Methane. Ooh, but methane is the parent name, so change it to methyl. What's the name of this 2-carbon group? That's ets or ethyl. And then in alphabetical order, the E is before the M. So this is carbon 1. And then we number the ring 2 and then 3, 4, 5. That'll get us to our branches as fast as we can. Cool. That was the hardest step, I think. Because once we're done, we had to already name the groups, the branches, to alphabetize them. So we already did step 4. We already named the branches. And by numbering the ring, we got the numbers for the branches too. So we'll just jump down to step 6 and construct it. Put them in alphabetical order, E before M. So the ethyl group is showing up on carbon 1. And the methyl group is showing up on carbon 3. The parent name, Cyclopropane. Nice. Not too bad, I hope. Let's go the other direction. Let's draw a structure from a name. So I'll have you draw 2 cyclopropyl butane. And that reminds me of something. So if you want to pause the video and name it, that's fine. But before we get started, perhaps go up here. I want to point something out. I've seen some people say, hey, of course, whoops, I don't want to write on the screen. Of course, the cyclopropyl group is stuck to the start of the chain. So some people just nickname this molecule cyclopropyl butane. They drop the number 1. And it turns out that's not a proper IUPAC name. You don't have to put the triangle group at the end of butane. You can put somewhere else. And because there exists another possibility, you must specify the position of that branch. So just get in the habit of always including your numbers. As we do more and more naming, you'll see that, wait a second, in a certain case, there is no other possible number. And so there are times that IUPAC rules will allow you to drop a number, the position of a group, when there's no other possibility. So if it's not ambiguous as to where that branch is, then it's permissible to drop a number. And people do it all the time on the internet and textbooks and stuff. I tell my students, don't even worry about when can you drop a number and when can you not. Just include them all the time. It's just extra detail. It's not incorrect. So sometimes you can drop a number and you'll say, ooh, is it wrong to put it in when you don't have to? And I say, no, go ahead and put in the number. Okay, go ahead and pause it. If you didn't get a chance to draw 2 cyclopropyl butane. I should have paused it too. Okay, I chose this one on purpose. what I'll have students sometimes do, it's a mistake, they'll say, okay, I'm going to draw the cyclopropyl group first, and then I'm going to stick on, let's see, butane is where there are 4 carbons, and I need carbon 2 to attach a triangle. So I will draw my butane like this and say, yeah, this is 1, 2, 3, 4. And that is not correct. Why isn't it correct? Well, one way to see that is, let's name this. Let's pretend we didn't know what the name was, and someone drew the structure and say, hey, can you name this for me? You would say, okay, step 1, find the longest chain or ring. Well, I like finding the rings first. It's right here. It's a ring of 3. Okay, what are my chains? Well, this is a ring carbon. It cannot be a chain carbon. So now I have a 1 carbon chain here and a 2 carbon chain. Yeah, okay, so there's no butane here at all. What is the name of this compound? Well, the longest chain or ring is a ring of 3 atoms. So the parent name is cyclopropane. Propane, 3 carbons in a ring, cyclopropane. On carbon 1, right, you want to number the ring to get to a branch as fast as you can. And hey, both of them are on the top carbon of cyclopropane, so that's carbon 1. Where's carbon 2, you ask? I don't know, who cares? You're not going to use a 2 in your name. So you can choose to be, you know, if you wanted to finish numbering the ring, you have 2 on the right side going clockwise, or you can have 2 on the left side going clockwise. Doesn't matter. There's no groups out there to identify. There is, however, a methyl group on carbon 1 and an ethyl group on carbon 1. It says right up here, put those groups in alphabetical order. So we're going to put ethyl first, followed by methyl. There we go. There's the name of that drawing. And that clearly, I hope clearly, is not 2-cyclopropyl butane. So how do you draw 2-cyclopropyl butane? I encourage students to read names backwards, meaning start with the parent, draw butane, and you can do skeletal. You can see I went to the top and zigzag down. You can start at the bottom and zigzag up, or you can draw your C's and H's, whatever you want to do. When you draw it, you decide how you want to draw it. I drew it this way. Someone else might want to draw it this way. Cool. They both work. They both get full credit on my exams. Okay. And then when you're drawing it, you get to decide how you want to number it. Some students like to start with number 1 on the left. Others will say, nope, starting on the right. That's perfectly fine. I'm drawing it, so I get to pick. I'm going to call this carbon number 2. And so here's carbon 2. And what I encourage students to do is, well, once you drew the parent, separately draw your branch. What's the branch? 3 carbons. I'm reading this backwards. So I start with butane, parent, drew it. Next is propyl, so I'm thinking 3 carbons. Anything special about this 3 carbon group? Yeah, lock them up in a ring. And that's an ugly ring. Try again. What's wrong with my hand today? There we go. This carbon, like we said, cannot be part of the parent because it's a ring carbon, not a chain carbon. And now connect the 2. There we go. Here's a good drawing. Decent drawing of 2-cyclopropyl butane. Nice. Looking at my notes, I think we're good. Moving on then. There's a new situation that happens when you have a ring that you don't have with chains, at least alkane chains. Let me just make sure I don't forget anything else. Nope, we're good. Because the carbons are locked into a ring, they're not free to rotate anymore. Right? So it used to be that single bonds were free to spin 360 degrees. And trouble here, sorry. When you lock up those carbons in a ring, well, now you disable their free rotation, right? So I'm looking at, look on the right side of the screen, got this carbon of the ring right here, and I got this carbon, and you might want to just rotate one of these carbons. I mean, that's a single bond. It's supposed to freely spin, but the ring is preventing it from rotating a full 360. They can wiggle and distort a little bit, rock back and forth, but that's it. So for me, being a visual learner, I more clearly see this drawing where the two bromines are close together, whereas this bromine is much farther away from that one. These drawings kind of show me that idea, the clearest. You know what? This looks like a funky chair. Like this part is a seat, and that's the back of the chair, kind of reclining. And then this bromine's above the seat of the chair, and this bromine's below the seat of the chair. They're on opposite sides. And these two bromines are above the seat of the chair. They're on the same side. And if you had some general chemistry, you may have been introduced to alkenes possessing the same kind of restriction. That is, double bonds are not free to rotate. So once you put groups on one side of the double bond, they're stuck there. And if you put the methyl groups on opposite sides, they're stuck there. They can't get across the double bond. So we got this group across from the double bond from that one. I like drawing a dotted line here saying, hey, this is the line you cannot pass. And these groups are saying, okay, we'll stay together on this side, the top side of the double bond. And then the prefix name, the way to nickname this or identify the fact, hey, the methyl groups are on the same side. The same side is we call it cis. CIS, which sounds like you're saying cis, short for sister. The pair of S's helps me remember same side, cis. And then if you go transcontinental, you go across the United States or across a continent. You translate, translocate, you go across. So trans means opposite sides. And we're going to use this same label over here when we name our molecules. I don't know if you can see that. Let's see if I can increase the magnification a little bit. A little better. Okay, so we have 5 carbons in a ring. If we want to name that, it would be cyclopentane. Have to name those 5 carbons, number those 5 carbons closest to a branch. Well, the branches are the bromine atoms. So one of these is carbon 1, the other one's number 2. Which one's which? Doesn't matter. We could have the closer one here be carbon 1 and the farther one be 2, or the far one is carbon number 1 and the closer one is number 2. Doesn't matter. There's a pair of bromos, dibromo, showing up on carbons 1 and 2. And they are together above the ring. They could also be below the ring. That is still cis 1,2-dibromo cyclopentane. If you attach the bromines on opposite sides, the 1,2-dibromo cyclopentane stays the same. We're just going to say, hey, the bromines happen to be on opposite sides. Okay, that's something to look out for. It is actually in our naming rules. So it's down here. There we go. In step 5, when we're numbering where they are, you'll just have to remember to add cis or trans anytime you have a carbon-carbon double bond, that's an alkene group, or whenever you have a ring. Those are the only 2 cases where you'll get cis and trans isomers. And then your name will require that. Well, it may require that. Let's do an example. Right. So, what if we need to name okay. like with triangles. Now, I'm not too good at drawing these sideways ones. We'll define that in our next video. Or maybe we should do it in this video. Yeah, we should do. Let's just do it. This type of drawing, where you're looking at the ring from the edge, this drawing is our normal skeletal drawing where you're looking above and down on the ring. And then we'll use dash and wedge bonds, right? So a wedge bond means towards us. So this wedge means toward. It's coming out of the screen, and then this dash bond means away. So literally, you're up here. This is supposed to be an eyeball. Those are eyelashes. That's awful. You're looking down, and then you see this broming away from you. That's why this dash line is drawn away. And then this broming over here is up above. It's coming towards us on a wedge bond. Okay, I'm more comfortable drawing skeletal drawing. So let's do that. Let's put a chlorine here, and then I'm going to draw a methyl here. Cool. All right, let's name it. Step 1, find the longest chain or ring. We have a ring of 3 and a chain of 1. Ring rings. Step 2, to name it. The ring has 3 carbons in it, so the parent name is Cyclopropane. Step 3, let's number it. Okay, number rings at a branch. So this carbon down here of the ring, or this carbon down here on the right side, one of them is carbon 1. Well, you break the tie by the second branch, so it's either going to be the chlorine on carbon 1, the methyl on 2, or the methyl's on 1, the chlorine's on 2. It's a dead tie. There are no more branches, so alphabetical order wins. Chloro is the name of the group on the branch on the left, and methyl, M, is the name of the group on the right, so C wins. This is carbon 1, this is 2, and then this has to be 3, but I don't even need that because there are no groups on 3. And the name, well, alphabetical order. So again, chlorine is first. So we got 1 chloro, 2 methyl. Named all my branches, separating my number from a letter, the dashes, and then cram the parent name Cyclopropane here, and then I feel like I'm done. But whenever you're drawing or naming compounds with rings or with alkenes, go back and ask, do you have a cis or a trans-isomer? And for rings, you actually get one more visual clue. What's this wedge bond and dash bond doing here? What are their purposes here? What's the purpose of having wedge and dash? To show that the chlorine is coming towards us and the methyl is going away. And that is opposite side, so we need the trans prefix out in front. The S next to a 1 requires a dash, right? Number next to a letter, you have to separate with the dash. Excellent. What if someone was not so careful? And remember, when you are drawing it, you get to decide how you want to draw it. So someone says, I'm drawing this. What's the name of this compound? Well, it's still going to be 1-chloro-2-methyl cyclopropane. But I can't tell whether the chlorine and the methyl groups are on the same side as cis, or if they're opposite sides. And that's as far as I can name it. So this name, 1-chloro-2-methyl cyclopropane, is a complete name. And then if you go in the lab and you find a bottle, it's probably a liquid, bottle of this compound, might be a gas, a container of this material, and it's labeled 1-chloro-2-methyl cyclopropane. It's a mixture of cis and trans isomers because both are possible. Sometimes the methyl and the chlorine atoms are on the same side. Sometimes they're on opposite sides. And we just have to say, okay, if this is the drawing we have, all the information, then we have to assume it's a mixture of both cis and trans. And there's actually 2 molecules here. Wait until our next few more videos. There's actually more isomers than 2. I'm not going to introduce chirality just yet. Let's see. Let's just take the last minute of our video to introduce one more thing. There is a name for this edge view type of drawing. So we have the normal skeletal drawing where you're overhead. There's this other type of drawing where you're on the side of the molecule. That's called a Hayworth drawing or Hayworth projection. And sometimes you can draw if it's a cyclopentane, you can just draw it normally like that. Or you can draw it from the edge like this. And sometimes you'll see drawings where they'll use a wedge bond to emphasize the fact that the tip of the cyclopentane's towards you, and then the other end of the ring's away. It's an edge view. But oftentimes, we get a little loose with that, and we just draw a regular pentagon. And then if someone uses these bond angles of 180, the hydrogen is 180 degrees from the bromine, that will inform you that this is not a normal skeletal drawing. This is a Hayworth projection. And what we're doing is we're emphasizing groups that are on one side of the ring or the other. So these 2 hydrogens up here are above the ring, and the 2 bromines are below. And if they're on the same side of the ring, bromines are on the same side, that's a cis isomer. Ooh, we're doing a little analysis here, not conformational analysis, because we're not going to change the shape. These are different molecules. They're in fact isomers. But the cis isomer is more crowded because the big bromine atoms, right? Where's the bromine on the periodic table? Is it from row 4 or somewhere? Lots of shells, lots of electrons, bigger atom. And if you get those big atoms spread apart farther, that's more stable. Less electronic repulsion. The electrons they're farther away, not repelling each other as much. Oh, I put in these canopy beds because again, I'm a visual learner. So when I see a Hayworth projection, I think of the bonds that are pointing down, being the foot of the bed, down here. And then the bonds that are pointing up, they're like the stems here, whatever, these boards that are holding up the canopy up above. Okay. A little note for us to be aware of for the future. In a later video, we're going to talk about something called axial bonds and equatorial bonds. And it turns out, if you have a Hayworth projection, you cannot decide which of these bonds is an axial or an equatorial bond. I know that doesn't make any sense now. We'll come back to this idea, but I thought, you know what? Anytime you see a Hayworth, just be a little careful if someone's asking you about axial and equatorial bonds. The information is not here in a Hayworth. Okay, I think that's a good place to pause. See you next time.